Welcome to BKW Physics. I'm Mr. McConnelly, and today we're going to continue our electrical talk. We've been doing static electricity, and we're going to move on to now electrical current. Flowing of electrons across the potential difference. So remember when we talked about a potential difference, that was in units of volts. 12 volts, 9 volts, 1.5 volts. And so when you had a potential difference, that was like the push, that's like the force. That's the best way to make an analogy of it. It's the force that will push the electrons. In a flow, just like with water, you can think of current like current in a stream. Current with an electrical circuit is flowing, but it's not water anymore. Now it's electrons that are flowing. So these electrons are flowing. And the electrons flow from high potential to low potential. So if you got 12 volts and 2 volts, it'll go from the 12 to the 2. Now, we have electricity in our bodies. There's electricity with thunderstorms. But there's also a huge infrastructure around the whole planet now of electrical circuits where we want to take the electricity, we want to use it for a purpose to do work for us. We got the lights on in the room. We got the computer plugged in charging. We got the computer over there, we got this over here, we got that plugged in there. We have so many electrical devices that need electrons all the time to charge up or to keep running, to keep doing work in physics terms. So you need circuits. And the most easy way to describe a circuit is a closed loop that electrons can flow through. So a demonstration of a quick circuit would be something like this. This represents a battery. This represents a light bulb, this represents a switch, and back to the battery. So what you can see here in my very basic diagram is that you have a potential difference, you have what's called a load, the thing using the electricity, and you have a control element, a switch. And then the electrons will flow around this circuit because it's a closed loop. But actually, right now, the way I have it drawn, would it actually flow the way I have it drawn? No. No, because I got the switch open. If I close the switch, boom, now it's a closed circuit. Electrons will flow. All right. That's concept there. Let's move on to a little equation that relates to this. So if you want to know, back up to current now, really. If you want to know how much current you are talking about, the reference table equation is stated this way, I being current. Now, you want it to be C, right? It seems like C should be current. But C, the unit C, is actually used over here, right? Because charge is in units of, remember, coulombs, right? So C's already been used for there. And the actual letter C as a variable is capacitance. So it's already used, so the next letter, I guess, that they decided they would use is I for current. It's a little awkward, but that's what it is. So current is with the letter I. Time, as always, in seconds, that's easy. So current should be in coulombs per second, right? Which it can be. But everybody uses a different term when they're talking about this. They use the term amps. Amps of current. Amps is abbreviated with a capital A. So really, for your notes, what I would highlight or star is that really when you're talking about current, you're going to be using amps, capital A. And to give you an idea of amps, just a relative idea, your house has electrical wires coming in, and then there's a meter someplace on a telephone pole right on the side of your house. And a typical house nowadays has 200 amps of current available coming into your house. 200. Okay? Now, in comparison, maybe like I'm trying to think of something small, like a little laser pointer that you were using in lab. That might use like 2 amps. Okay? So 2 amps versus 200 amps. I'm trying to give you like the range of things so you can kind of see there's a large range. But remember what it means. It means how many coulombs per second. And remember what coulombs means. 1 coulomb is how many dump trucks of sand grains counted. 20,000.
close.
Okay? Not even close. Alright, so if you sat there and counted sand grains at 20,000 trucks, which is an impossibility, you would come up with this number, this 6.25 E18, huge number. That's how many coulombs per second. So 1 amp is that many coulombs per second. I'm trying to give you a frame of reference so you can kind of put it all together in your mind. Where can you go with this? Well, now you know the flow of electricity. You know there's potential. Well, I wonder how much power we might be talking about. Remember, we did power earlier in the year. And when we did power earlier in the year, how did we define it? Power was equal to what? It's hard when I have to review. I didn't caught you off guard. When we ran up the stairs, and we figured out the time and the work. It was work divided by time. This was our original equation. It's still going to be true. It's just going to get changed a little bit in that you have to find things differently. So, last chapter we were just working on how did you get work when you're talking about electrical work? Well, you got it by taking the potential and timesing it by the charge, which is also in your reference table, but it's written in a different order. It's written as V is W over Q, but this is in your reference table. So now if we join the two, we say, okay, then power must be equal to potential times charge over the time. Not quite done yet, because what is charge over time? Amps. So, power, this now turns into the letter I. And I'm writing it in a different order because this is the way they write it in the reference table. So this went right to there. This is a new reference table equation. And what it says is that the potential, which is in what units again? Potential is the push. Volts. So potential is how hard you're pushing in volts. This is the current, which is the flow, which is in what units? Amps. A. So a volt times an amp is power. And you could write volt times amps and you wouldn't be wrong, but no one does that because power is in units of watts. Yeah, watts. Just like it was before. So you have power, P is IV. This is in your reference, this is in your reference, this is in your reference. Along with this one right here. They're all there. I'm just connecting the dots for you because they're not all right next to each other. So for today, physics.